The digital twin simulation generates a computer-generated underwater scenery, for example, randomized benthic cover varying in location, size, and counts to train and test AI computer vision algorithms. A digital twin is a digital model of an intended or actual real-world physical product, system, or process, a physical twin. In computing, procedural generation is a method of creating data algorithmically as opposed to manually, typically through a combination of human-generated content and algorithms, coupled with computer-generated randomness and processing power. In computer graphics, it is commonly used to create textures and 3D models. Procedural content generation can be applied to a variety of use cases, ranging from maritime application, for example, harbor safety, to agriculture. This slide introduces the challenge of mapping seafloor benthic cover, which is a critical foundation for creating a digital twin of an oyster farm. On the left, we see an example of habitat mapping around Crete Island, where survey points indicate seagrass presence and other ecological features. These types of maps provide essential input for digital twinning models, as they capture the real conditions of the seafloor environment. On the right, we see examples of the ecosystems involved, seagrass meadows that support biodiversity, and species such as turtles that rely on healthy benthic habitats. For oyster farms, similar environmental data is crucial to simulate ecosystem interactions, predict growth conditions, and support sustainable aquaculture. However, producing accurate benthic cover maps is costly and time-consuming. This is where procedural content generation can help, by using algorithms and models to generate realistic, data-driven representations of the seafloor, reducing costs while still supporting reliable digital twin simulations. This slide goes a step further into seafloor benthic cover mapping by showing detailed transects of seagrass presence. Each highlighted area represents a survey section where benthic data was collected, mapped, and overlaid with satellite imagery. For oyster farms, this type of fine-scale mapping is extremely valuable. It helps identify suitable farming sites by showing where seagrass beds are located, how they interact with water flow, and how the farm may impact or benefit from nearby ecosystems. As we can see, the mapping process involves breaking the coastline into smaller survey grids. While accurate, this approach is labor-intensive, requiring divers, remote sensing, or drones to gather data. Again, this highlights the potential role of procedural content generation. Instead of relying solely on costly field surveys, we can generate realistic benthic data to feed into the digital twin of an oyster farm, ensuring both environmental accuracy and cost efficiency. This slide shows what the mapping looks like in reality. Here we see underwater imagery captured from transects. These ground truth photos reveal the actual benthic cover, such as seagrass beds and rocky habitats, confirming what was detected through mapping and satellite overlays. For oyster farm digital twinning, this level of detail is critical. It not only validates habitat models, but also provides the textures and environmental conditions that influence oyster growth, water quality, and ecosystem interactions. However, capturing this kind of high-resolution underwater imagery requires divers, cameras, and extensive fieldwork, adding to the costs and logistical challenges. By integrating procedural content generation, we can reduce reliance on costly underwater surveys, while still creating accurate and realistic benthic layers within the digital twin of an oyster farm, making simulations both scientifically reliable and more accessible at scale. Here, we introduce OyTwin, our approach to applying procedural content generation for the digital twinning of oyster farms. Instead of relying only on costly and time-intensive field surveys, OyTwin can generate computer-simulated underwater environments. For example, it creates randomized benthic covers, varying in location, size, and density that resemble real seafloor conditions. These virtual environments allow us to train and test AI computer vision algorithms for benthic mapping. The advantage is clear. We can accelerate development while dramatically reducing the cost of data collection. On the right, you can see how OyTwin integrates multiple perspectives, from the environment view to bottom and front cameras, sonar, and depth sensors, simulating what an autonomous underwater vehicle would see. This makes it possible to build a scalable, low-cost pipeline for seafloor mapping, directly supporting the digital twin of an oyster farm. This slide gives a technical overview of OyTwin, showing the tools and features that power the system. On the technology stack side, OyTwin uses headless Blender for 3D rendering, combined with Python to control procedural content generation. For detection, we integrate YOLO v4 object detection, which can automatically recognize oysters and benthic features in the simulated scenes. For hardware interface, OyTwin is designed to work with Blue Rove through ROS, the robot operating system. This allows the simulated digital twin to mirror how a real underwater vehicle would behave. We also simulate range scanners, such as sonar or LiDAR, for obstacle detection and mapping. In terms of key features, OyTwin can randomly generate underwater terrains, complete with rocks, sand, and elevation. It can also procedurally place oysters, varying their counts and locations with configurable parameters to model different scenarios. Finally, the simulation environment allows control over water clarity, lighting, and terrain complexity, making it possible to replicate a variety of underwater conditions. Looking ahead, we see the potential to combine OyTwin with large language models, enabling dynamic scenario generation and adaptive digital twin simulations. This slide provides a more detailed look at the technical stack of OyTwin, focusing on the software libraries and custom modules that drive the system. On the left, you can see the standard Python libraries we use, such as SYS, subprocess, OS, and JSON. These provide the backbone for file handling, system operations, data parsing, and logging. On the middle, we have the third-party libraries that extend Python's capabilities. For example, BPY integrates with Blender for 3D rendering. NumPy and Torch handle numerical and machine learning tasks, while TriMesh manages 3D mesh operations. Libraries like Plotly and PyHocon are used for visualization and configuration. On the right, we have local and custom modules developed specifically for OyTwin. These include Simulate for motion dynamics, Sonar and Range Scanner for simulating acoustic and LiDAR-based sensing, MU-Utils to generate sensor readings like acceleration and gyroscope data, Utils for positioning, rendering images, saving values and plots, and Create Scene, which procedurally generates the environment, from deleting objects and creating landscapes to adding oysters, lights, and water. Together, these libraries and modules form the foundation of OyTwin's digital twin framework, enabling realistic underwater simulations for oyster farm environments. This diagram gives a high-level workflow of OyTwin's technical pipeline. It starts with the environment setup, where the 3D underwater scene is initialized. From there, we configure the sensors and simulation parameters, followed by setting up the simulation components. This is the simplified end-to-end simulation pipeline of OyTwin. We begin with the environment setup, initializing Blender and required packages. Then we move to scene initialization, where the underwater landscape and add-ons are loaded. Next, in sensor and simulation configuration, we define the cameras, motion paths, and other parameters. After that, the simulation component setup integrates the Blue Rove and seabed models. The system then enters the main simulation loop, where the Blue Rove moves, sensors update, and images are rendered. Finally, all this is exported in the data output stage, giving us rendered images, pose data, and sensor logs for downstream AI training and analysis. And that brings us to the end of the presentation. Thank you for your attention.